Hello everyone. I'm going to go over the practice project for chapter 9 part 2. So for this first question we have a company's total sales in millions of dollars T months from now. Okay, so it's in the form S of T. And for this first question we want the total predicted sales 7 months from now. So what we're going to do is we're going to plug in 7 to our original function that models the total sales. So that's just 0.02 times 7 cubed plus 0.57 squared plus 2 times 7 plus 3. Right? You can put that in the calculator and you should get 48.36. Now one thing to note that S is in millions of dollars. So notice how question 1, it just says dollars. So then that means we have to multiply by 1 million to get it on the same unit. So our answer should be $48,360,000. Okay. For the second question, we want to know the instantaneous rate of change of S of T from 9 months from now. So this means that I need the first derivative because that's an instantaneous rate of change, and we want it when T is equal to 9. So first we need to find S prime of T. Okay, so you can't plug anything in yet. You need to find the derivative first. So we can split them up because these are all being added. So the derivative of 0.02 T cubed is just 0.02 times 3, use the power rule, right? 0.5, and then times 2T, and then derivative of 2T is just 2, and then the derivative of 3 is just 0. So that's going to be our derivative. You don't need to simplify if you don't want to, because we're just going to go ahead and find S prime of 9. But if you like simplifying, that's fine too. So we're just going to plug in 9 wherever I see a T in my first derivative. Right, and go ahead and plug that in the calculator, and you should get 15.86. And notice that part of the answer says in millions of dollars. So here we don't need to multiply by a million. So our answer is just 15.86. And question 2 kind of gives away the answer to question 3, just because it's basically the same thing. We're just plugging in a different number. So the answer is millions of dollars per month. If we didn't have this in question 2, we can also look at question 3 as in S prime of 13 is equal to ds dt. Right, we're taking the derivative of our S with respect to time t. And so we know that the units of S is millions of dollars. And then our unit time t is months. So that's how we get the millions of dollars per month. All right, let's move on to question 4. So we have a price-demand equation. X is a function of the price. And so with these constants, we have the price-demand X equals 11 plus 230 over P. And we want to find the instantaneous rate of change of demand with respect to price. And we want to know when price is equal to 4.19. So we want to find the instantaneous rate of change. So that's going to be our derivative. And this is going to be the derivative with respect to price, which is our P variable, of 11.230. I'm going to rewrite this P as P to the negative 1 power. And so let's take the derivative. Derivative of 11 is just 0 plus 230. We can pull that constant out and just take the derivative of P to the negative 1. Go ahead and use that power rule that we've learned about in this chapter. All right, and so we can also rewrite this as negative 230 over P squared. So that negative means I can put it in the denominator and make the power positive. So that's going to be our x prime, and we want to know what's my x prime when p is equal to 4.19. So all I do is just plug in 4.19 into my p variable. And so this one gives me an answer of negative 13.1, and round to the nearest hundredth is that. All right, and it's okay that it's negative because this is a rate of change. It's not a certain amount of pounds of chocolate. It's not a certain amount of dollars. This is a rate of change, so it could be positive or negative. Okay, so now we have a college enrollment question where we have years and the percentage for females. And so we want to build this cubic regression model shown here in order to answer questions 5 and 6. So I'll hop onto Desmos and show you that real quick. All right, so I'm going to show you how to do this in Desmos. So let's grab our data real quick. You can just copy and paste it very conveniently. Paste it into this cell. It'll automatically generate the X and the Y like so. But for this problem, our X is the time in years since 1970. So all we have to do is just subtract off 1970 from each of these X values. So the first one, 1970 minus 1970, well, the difference between the two is just 0 years. 1970 versus 1980 is a difference of 10 years, and so on. And 1970 versus 2010 is 40 years. Okay. And for this one, we want to build a cubic regression model, which takes the form as y1, which is our output. Use that tilde, and then it's going to have the constant a x1 cubed. That's our first term, plus x1 squared. That's our second term. And then x1 plus d. So that's our cubic regression. And then all we have to do is just find what the constants are to make our final form. So here we have to note the rounding because that can make a big difference in your answers. So we want A to 6 decimal places, B to 4, C to 3, and D to 1. So if we use those rules, then we just round this first one, our A, to 0.467. Sorry, 0.00467. Right? So it's like this second 6 that gets rounded up. For B, so let me put in our x cubed. So our B is to 4 decimal places, so that will be the 6 right here, but the 4 isn't going to make it round up, so we'll just take 0.0276 x squared. And then C is to 3 decimal places, so this 5 will get rounded up because of that 9. So plus 0.266x, and then our last constant D is just to 1 decimal place, so that's at 4. That will get rounded up because of that 6, so 25.5. And this is our regression model for questions 5 and 6. Okay, and so from Desmos, we have this model here, y equals negative 0.00467x cubed plus 0.0276x squared plus 0.266x. Running out of room. And then our last constant is 25.5. So that's going to be our cubic regression model. in order to answer these next questions. So we want to use the model to predict the percentage of female high school graduates in 2021. So our model, which is a function of x, like this, right? So x is our time in years since 1990. So I need to do the same thing and bring it to the same scale by subtracting 1970, not 1990. And so we can subtract that, and this would give me 51 years, right? There's 51 years between 1970 and 2021. So I want to find y, which is my model, when x is 51. So all I do is just plug it in. Oops. 0.467 times 51 cubed plus 0.027651 squared plus 0.266 times 51 plus 25.5. So when you throw that into the calculator, you should get 48.9. And so that's our answer here. And this next question, it's asking to predict the instantaneous rate of change. So whenever you hear those words, you should think automatically derivative. So we're going to need y prime. And let's see, we want to know this in the year 2017. So we're going to do x is equal to 2017 minus 1970. And this gives us 47 years in between. So we eventually want y prime of 47. So first we should find y prime with respect to x. So you can pull out that constant again, and then the derivative of x cubed is just 3x squared plus 0.0276 times the derivative of x squared, which is 2x, and then plus 0.266. And so now let's plug in 47 wherever I see an x in my first derivative. Okay, just be careful with the parentheses and plugging it into your calculator. Plus 0.26, oh no. Plus 0.266, and this gave me negative 0.23. So a negative 0.23% per year. Okay, for question 7, we have an advertising question. So we are given this formula here that says that we'll sell N units of product after spending X thousand of dollars in advertising, given by this formula here. So we want to use differential approximations to estimate the increase in sales that results by increasing the advertising budget from $10,000 to $10,578. So one important thing to notice here is that our X here is in thousands of dollars, right, as indicated in the first line. So we should first convert these to X thousands of dollars. All right, so to do that, one way you could do it is you can divide these two numbers by 1,000, or you can just think of this as 10,000 or $10,000, whichever way works for you. So we want to know the increase in X equals 10 to X equals 10.578. And again, you can think of this as 10,578 divided by 1,000 for the thousands of dollars. Okay, so we're going to need to know what's the increase in sales when we make this change from X equals 10 to 10.578. So let's recall our differential approximations formula where dn equals n prime of x dx. All right. So this n prime of x, this is going to be our derivative at our original x value, which is 10, which we just calculated, right? And then dx means the change in x. So that's kind of described here. And the way that we write the change in x, we just subtract the two. The new minus old. All right, so the last piece that we need is what is n prime of 10? So we can find that fairly easily. So first we need n prime of x. And so that just means I want to take the derivative of this n formula. You can think of it as n as a function of x, if that helps. But I want to take the derivative of n with respect to x. So let's do it term by term. I have the 63x. When we take that derivative, we get 63. And then I have a minus x squared, so we can use the power rule. Bring the power down and decrease it by 1. So the power is just 1. And then lastly, I need to plug in 10 wherever I see an x in my derivative to get the derivative when x is equal to 10. So that's what I'm gonna do. And if you calculate this, you should get to 43. And so I'm gonna plug this back into my differential approximation and put 43 here. And then when you calculate this difference, you get 0.578. And so our estimated increase in sales comes out to be 24.584. And the very last thing you need to do is check how we're going to round this number, if we are at all. So we want to round to the nearest integer. So because it has this 5 here, we're going to round up to 25 as our answer. Okay. Average cost now. So we have a cost function here, and we want to estimate the change in average cost if we increased production from 20 to 25. So this is going to look like our DC average is going to be C average prime of x times dx. And more specifically, we want to know from 20, if we increase 20 to 25, what's going to happen to my cost. So we're going to need C average first of x. So they kind of reminded you that you can just take the cost function and divide by x. So that looks like this. All right. Now if you wanted to take the derivative and do the quotient rule, that's fine. You should get the right answer if you do it carefully. I, on the other hand, do not like dealing with quotient rules, so I'm going to try to simplify a little before taking the derivative. So I can break up this fraction into smaller fractions because there's addition in between each term in the numerator. So it would be broken up like this. And then an x in the bottom can cancel with an x in the top because there's multiplication here. And for the same reason, I can cancel these x's. And so my C average of x is 0.46x plus 6 plus 391 over x, which I'll just write as x to the minus 1 power. And so I want C prime average, or C average prime, and that's just taking the derivative of the previous line, so 0.46, and then 6 just goes to 0 when taking the derivative, so then we add the 391, and then power rule the x to the minus 1, so like that. Alrighty, and you can rewrite that if it helps you. You can simplify if it helps, so like that. You don't need to if you feel comfortable working with the first form. So now let's find C average prime of 20. So again, let's just plug in 20 for x. And this gave me 0.5175. I wouldn't round. I mean, this comes out to a whole number, but if there was a case where you had to round, just round to maybe 4 or 5 decimal places just to avoid rounding error. So I'm going to plug in that quantity here. And then the difference or change in x is just 5. And so my answer is going to be negative 2.59. We're going to round to the nearest cent for this question. Okay, question 9. Again, another differential approximation. Now we want to know the change in profit if production is increased from 1500 to 1589. So again, dP is equal to P prime. And so when I say this P, this is going to be my profit. My profit. Whereas the smaller P is my price from the price demand. But I don't think that comes into play here. But anyway, that's just the notation I'll use throughout this class. Again, we want P prime x dx. So for here, P prime of 1500, that's my starting x. And then I want my change in x. That's 1589 minus 1500. So I need my price function first because all I have is my cost and revenue. But we know that price is equal to revenue minus cost, so we can find that real quick by subtracting the two. Okay, plus 61x. So we can simplify a little if you want. Again, not necessary, but sometimes it makes things easier. And this becomes minus 61x because of this minus. And then you can combine 206x minus 61x to be 146x. And then I think that's as simple as we can get it. Oops, 3, 0. Okay, P prime. Let's take the derivative now. That's just going to be 145 minus 0.059 times 2x. And then I want P prime of 1500. So 145 minus 0.059 times 2 times 1500. And so this gives me negative 32. So let's plug this over here. Negative 32 times 89. That's my change in x. And this comes out to be minus 2848. Alrighty. Question 10. So this marginal profit question, we're given two statements here that talk about the weekly demand and what the price was. So these kind of form points. 292.14 and 207.16. We also know that we have fixed costs of $13.92 and a variable cost of 4. And then we can assume that the relationship between price and demand is linear. So the relationship between these 2 points are linear. And what do we know about a line between 2 points is that they have a slope. All right, and the slope is just y1 minus y2 over x1 minus x2, or however you learned it. The order does not matter as long as you keep the pairs together. So here I'm going to do 14. I'm going to do 14 minus 16 over 292 minus 207. And so this gives me minus 285. As my slope. And so to make my relationship, my price demand function, that's just going to be a line. I'm going to use the point slope formula that looks something like this. And so we can use one of our points, say 292.14, where this is my x naught and this is my p naught for my specific point. And I'm just going to plug them in with my m. So p minus 14 is equal to minus 285x minus 292. So we can do some simplifying. Let's get p to one side. So minus 285x. Let's see, I think this comes out to be 584.85. You can also just calculate these as decimals if you want. Just be careful with rounding. And then plus 14. And so you can further simplify and get 1774 over 85. Okay, so that's our price. So that's lowercase p in this case. And it's a function of demand, which is our x. All right, we also know that the cost is linear. So our costs here are our fixed costs, $13.92, plus our variable cost of 4. And variable means that it is the cost per one item. So if we want to know per X items, we have to multiply it by how many we sell. All right, so that's our cost. And so we are asked to predict marginal profit. So this is going to be my capital P now, where marginal profit is P prime of 256 when we're selling X equals 256 toasters. All right, so we need P as in profit because we weren't given it. One thing we do know is our price, lowercase p, and we know that revenue is a function of price. So that's just X times P, our lowercase p. So we can just multiply what we found for P by X. So this gives us minus 285x squared plus 1774 over 85x. And so the last thing to do is just, well, second to last thing is to form our profit function. P is equal to R minus C, our revenue minus cost. So that's the revenue function that we just found, plus 1774 over 85x, minus our cost, which we found before as 1392 plus 4x. All right. And so you can simplify this slightly. You don't have to simplify it fully if you don't want to. I'm just going to distribute that negative in because we'll need to take the derivative in the next step. So now let's find P prime, as in our profit of X, so just the general derivative of P that we just found way at the bottom. So that's going to be 285 over, so derivative of X squared is just 2X. And then the derivative of 174 over 85x is 1774 over 85. And then this goes to 0, right, because that's a constant. And then this derivative is just minus 4. So that's going to be our profit function, or our marginal profit. And now we want to find the marginal profit when x is 256. So we're just going to plug in 256 wherever I see an x, plus 1774 over 85 minus 4. So putting it into the calculator, I get 4.82 as my answer. Okay. All right, so break-even analysis. I already made a video on questions 13 and 14, but I'm happy to go over it again, especially to answer 11 and 12. So I'm going to hop over to Desmos again and show you how to build the linear regression models for our price and our cost function.
Okay, so let's do the last problem. This is on the break-even analysis. I already made a similar video on this, but we can just go over it one more time. So I'm going to grab the data and I'm going to just dump it right into Desmos. It auto-generates it, which is nice. And so what do we want? So we want to find a linear regression for the price demand, and then we also want a linear regression for the cost. Okay. So I'm gonna rename this. This is my price, and this is my cost. This is my demand. So let's first make the price one. So P1. So it's a linear function, so I'm just gonna have AX1 plus a constant B. And then for our cost, I'm gonna have so we'll do a C X1. We'll use different letters plus D for the constant. So this is what I get. And so we want a linear regression. Let's look at how we have to round. We want A to 1 decimal place, and B is rounded to the nearest integer. So looking at my first one, I get A to 1 decimal place, which is already there, negative 0.2 x plus, and then we'll round up that B to 2007. Hopefully this looks kind of familiar to you. And then for our second one, I have the nearest integer, I believe. Nearest integer and the nearest tenth for 10,000 for D. So C is 282x, and it's a linear function. And then again, we have this scientific notation, which basically means to multiply it by 10 times 6, which is 1,000,000. So it looks like 2. So we just move that decimal point over 1, 2, 3, 4, 5, 6 times. So we'll go here. So that's how we have 2,825,500. And so to the nearest tenth means that I want to round to this place. And so that 5,500 makes my 10,000 go up to 3,000. Or 30,000. 30,000. So that's how we round D for this question. Okay. And I think we'll come back to this, but for the break-even points, we're gonna need our revenue, right? Because for break-even, that's where our revenue is equal to cost. So revenue is X times our price function, which is here. So we will eventually need to do X times this. But we will. Let's go ahead and answer the questions for part 11 and 12 first.
Okay, questions 11 and 12, they have to deal with costs for the cost data, right? And so from Desmos, we found that cost is equal to 282x plus 2,830,000. So for the question 11, we want to know the fixed costs. So these are the costs that are there no matter how many treadmills, I suppose, we sell. So whether we sell 0 treadmills or 100 of them, my fixed costs are always going to be this amount. It's fixed, right? So this is going to be 2,830,000. And then for 12, we want the variable. So this is the cost that will change depending on how many treadmills we sell. And that comes from this term of our cost function. So this will be 282. Okay. And for our last 2 problems on this project, you had to find the break-even points. So I'll go back to Desmos and show you how to do those real quick.
Okay, so now we want the break-even point. So as I hinted previously, we're going to need our revenue, which is X times P. That's what we found here. And we want to know when is it equal to my cost, which is modeled by this function. And so graphically, this means where do these two curves intersect? Those will be our break-even points. So we want to find the first point of intersection. So I'm going to, let's ungraph these. And then this is kind of hard to see, so I'm just going to plot it in a different color. I don't think I can change colors, so I'll just plot it in a different line. So yeah, so now we're looking at the blue versus red curves. So the blue is our revenue, the red is our cost. So we want to see where the two intersect. So this will take a little bit of manipulating because the scales are very different between your price and cost. So gotta be patient with this, like I showed you in the other video. I believe it's the exact same numbers too, because I think I did the practice project. But anyway, so intersection probably somewhere around here. So you can just click anywhere and see if a gray dot appears. And so that is our first point of intersection. So this is our smaller breakpoint of the two. All right, so that's one. And so another one would occur to the right of this because we know that the red graph is to the left of this blue part of the function. So at that point that we just found, it crosses over to the right. And so we know that it kind of, the red line, if we like zoomed out really far, the red line would go through here, which is the one that we found, and then another point like this on the right hand side of the blue function. So that's the one that we want to find next. You can kind of see the red curve starting to go close to the right part of the blue function. And maybe that's happening around here, so I'll zoom in a little. Maybe about here, so I'll click and see a gray dot, and there we go. And that's our second break-even point. And so we just want to make sure that we're rounding to the right decimal place, and that will be our answer.
And from Desmos, we found the points 2,204 rounded to the nearest treadmill, which means integer, and the larger one is 6421. All right, so we have just finished going over the practice project for, again, Chapter 9, Part 2. And I hope you found this to be really helpful. See you at the next one.